Hello, my name is Chandran Park, and today I'll be talking about the fascinating but also frustrating world of NP-hard problems. At this point in your computer science journey, you would have encountered a variety of problems, which we have tackled with some sort of strategy or algorithm, such as searching through an array just by looping over all the elements in order, or sorting input through comparisons of adjacent elements in bubble sort, and many more that use graphs and trees. A very important goal that we have worked towards is to reduce the time complexity of these algorithms, making them as efficient as possible, such as using binary search over a regular loop for sorted arrays, or using merge sort over bubble sort, achieving n log n rather than n squared. A commonality amongst these algorithms is that the time complexity has always been polynomial. So basically, this is just a math term saying that the time complexity falls under O of nk, where k is some constant integer. In general, these algorithms are considered easy and efficient, because with the immense power of computers, even the highest polynomial algorithms can be solved rather quickly. But it turns out, sometimes we are just not that lucky, and some problems are simply hard, with no algorithm that can solve them in polynomial time. And this is where NP-hard problems come into play. NP-hard problems are just problems that are at least as hard as every NP problem. Now, unless p equals np, which is the million-dollar problem no one's been able to solve, all of these problems will be very difficult to solve, needing exponential or even factorial time to solve, and sometimes they won't even be solvable at all. As you can see from the diagram, all of these NP-hard problems are harder than any of the p problems that we have solved in the past, and by looking at the graph on the right, which plots input size n with their respective functions, clearly, harder problems that take factorial or exponential time will be much more arduous with large input sizes, and even the strongest computers will struggle to compute them efficiently. Now, this is all well and good, but how can we tell if a problem that we've encountered is truly an NP-hard problem, or just a particularly difficult p problem that we can solve in polynomial time? Well, the first NP-hard problem proven is called SAT, which was proven to be at least as hard as every NP. However, doing this for every NP-hard problem would be difficult. So instead, we use a different trick called reduction. By taking a known NP-hard problem, seen on the left, and transforming them in p time into our problem, we have proven that our problem is also NP-hard, as long as our two problems have the same solution. Why is that? Well, let's suppose the opposite case and our problem is not NP-hard. That means our known NP-hard can be converted to our problem in p time and then solved in a time that is not as hard as every NP. However, this makes the original NP-hard problem not NP-hard, a contradiction. A quick example of this is reducing an independent set problem to the k-coloring problem. Clearly, if vertices could be put into k-independent sets, each set could be colored differently and the graph would be k-colored, as the same colors, being independent, won't be adjacent. Which is why, as we reduce the independent set problem as shown, which can be done in p time, just changing the goal to be k-coloring, we showed that k-coloring is also NP-hard. But at the end of all this, you might be wondering, why does knowing that something is NP-hard matter? Well, sometimes problems we encounter will just be hard, with no ways to create efficient algorithms. Being able to prove that a problem is NP-hard lets you know when to move on from endlessly trying algorithms, instead trying to estimate within a range or just using smaller inputs so the time taken doesn't blow up. Thus, knowing about NP-hards and reduction is useful to identify a problem that is too hard, allowing you to focus on other alternatives.